BTEC Applied Science, Unit 1 Chemistry paper. Second one I've done. This is from a sample assessment. So it was basically before the course started, I had a sample paper. Anyway, it's a proper paper. Let's have a go. As always, write neatly in black pen. Bring a ruler. Bring your own calculator. Bring your own calculator. I'll say it once more. Bring your own calculator. Yeah. Look at how many marks there are for the question. If you haven't got a clue, leave it. Come back later on when there's a few minutes left and write something down. Try to write something sensible down. 30 minutes should be enough, but you don't have time to relax. Basically what it says on the front of the paper. They used to have the three papers together. Now they've split them up. You'll be given a periodic table, which you will definitely need. Okay, you should be familiar, particularly with the first 20 elements. It's always a good idea, I think, learn the first 20 elements, be able to write a little mini periodic table of the first 20 elements. When you're doing this video, I suggest you actually have a go at the questions before you see my answers. It'll be a much better way of learning. So pause the video, have a go at the question, and then look at my answers. Let's begin. Nitrogen reacts with oxygen in car exhaust to produce nitrogen 4 oxide. Nitrogen 4 oxide is a gas that can cause air pollution. Some of the properties of nitrogen 4 oxide are dependent on the electronegativity of each of the elements it contains. State the meaning of the term electronegativity. After all of that waffle, what does electronegativity mean? Well, it is, there you go, in a molecule, how attractive an atom is to the electrons involved in the bond. Okay, I'll explain that. In other words, let's say you've got something like hydrogen fluoride. Okay, and basically your hydrogen fluoride, there's an H and there's an F, and it's a covalent bond. So they're sharing a couple of electrons, but basically the fluorine atom is much more attractive. And so what you'll find is that these electrons will spend a lot more time hanging around the fluorine than they will around the hydrogen. And because of that, you'll end up with what we call a polar molecule. In other words, that end of the molecule will be positive and that end of the molecule will be negative. So it's a polar molecule because the fluorine is more attractive to the electrons in the bond, in the covalent bond. And this nitrogen 4 oxide is actually, it's nitrogen dioxide. I don't know why they call it in here, you know, they're just making it hard. So you've got your nitrogen and you've got your two oxygens, right, like that. Okay, and basically it again, there's a difference, and I think we're told it in the next question. There's a difference in the electronegativity, so the electrons spend more time around one atom than the other. Figure doodah shows the variation of electronegativity with atomic number for some of the 40 elements, and it says describe. That's our command word. It doesn't say explain, it says describe the trends in electronegativity in the periods and in the groups. 1 mark for each probably. So the trends are now in a group, like so here you've got fluorine, chlorine, we haven't got bromine and iodine, but going down a group, yeah, they're in the same group, they're in group 7, the electronegativity gets less. Along a period, so if we have a look at period 2, from lithium to fluorine, there, the electronegativity increases. So in a group, yeah, electronegativity decreases as we go down the group. In a period, from left to right, electronegativity increases as we go left to right. It's not asking us to explain why, it just says describe. State the three factors that affect the electronegativity of an element. You know, why are some atoms more attractive to these shared electrons? And the answer is 3 marks, so 3 different things. Okay, how many protons there are in the nucleus? If you've got more protons in the nucleus, then the electrons are going to be more attracted to that nucleus. The radius of the atom, okay, again, it doesn't ask us to explain, it just says state, but the radius of the atom, the smaller the atom is, then the closer the electrons will be to the positive nucleus, so there'll be more attraction. And how many shells the atom has, because the shells, well as making the atom bigger, the shells actually shield, so there's less force, there's less attractive force if you have another shell of electrons. So there you go, 3 factors which affect the electronegativity of an element. Nitrogen 4 oxide is a gas which dissolves in water in the atmosphere to form acid rain. Totally irrelevant. Electronegativity of nitrogen is that. Electronegativity of oxygen is that. So going back to my NO2 molecule, there's the nitrogen, there's the oxygen, okay, and there are the bonds there. Now the oxygens are more electronegative, and so that means that the oxygens will be slightly negative compared to the nitrogen. So we'll have a bit of a polar molecule going on here. Okay. Now explain the 2 types of intermolecular force. Now intermolecular, this is the key word here. I'm not interested in the covalent bonds. I'm interested in the bonds between the molecules. So if you've got one NO2 molecule there, and let's say you've got another NO2 molecule there, now it's the bonds between the molecules, and the most important one will be this one here. It's a little bit like, do you remember hydrogen bonds? Yeah, do you remember hydrogen bonds? And it's this dipole-dipole bond. Okay, so the molecules are, and this one says explain, so we need a little bit more than just saying what it is. So the molecules are polar, and so you'll have the positive ends of the molecule attracting the negative ends of the molecule. And this is a permanent dipole. So there'll be a permanent dipole-dipole bond. There'll also be some temporary bonding, because the electrons don't always stay in the same place. They're kind of shuffling around randomly. Every now and then there will be temporary, like instantaneous dipole-dipole bonds. So there you go, pictures in the way. The nitrogen 4 molecule is polar because of the difference in electronegativities. Because of this, there will be permanent dipole-dipole attractive forces. There will also be temporary dipole-dipole forces due to the variation in the distribution of the electrons. So permanent and temporary dipole-dipole bonds. Understanding the electronic structure of chemical elements allows scientists to predict how they will react. Which of the following elements has this electronic structure? So which element is this? So how many electrons have we got? So we've got 1, 2, 3, 4, 5, 6 electrons. So look on the periodic table. Hairy Henry likes beer by cupfuls, so we're talking carbon. So that is carbon. Carbon's got 6 electrons. Silicon has 4 electrons in the 3rd energy level. Explain the arrangement of the electrons in the 3rd energy level of silicon, 3 marks. So let's figure out what's the electronic structure of silicon, and explain it. So silicon, look on the periodic table, has 14 electrons. Yes. So how are they going to be arranged? So in the first shell, we have one s2. Okay, and that's just one orbital, which is there and there. And then that's the first shell. In the second shell, we have two s2, which is there, and then that one fills up. Okay, and then 2p6, and 2p6 goes 1, 2, 3. They call it actually XYZ, and then that and that and that, in that order. It fills up in that order because it takes less energy to do so. It's always higher, going up from shell to shell, going from subshell to subshell, and when you fill up the electrons, it's always a higher energy state, if you know what I mean. So that's n equals 2. That's the second shell. Now we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We've got 4 more electrons, and this is getting on to the third shell, which is what it asks for. Okay, so the third shell is going to be 3s2. By the way, I should put a 6 there actually. 3s2, which is there and then there. So in that subshell, there's one orbital, 2 electrons. Then 2 more electrons, and they go in 3p2. And as I just said, it goes that one in the X, and then that one in the Y. And this one here fills up before that one. Yes. Why? Because I said it's in order of energy. This electron is in a lower energy state. This electron is in a lower energy state than that one would be. So that fills up first. Okay. And as I said, if you want to, we can call these X, Y, and Z. Okay. Let's just get rid of that. Yes. And so n equals 3. N equals 3 is this, and that's what it's asking for in the question. Explain why the first ionization energy of silicon is greater than that of germanium. Okay, now we can explain this. First of all, let's have a look whereabouts these are on the periodic table. And if you look on the periodic table, you'll see that silicon is above germanium. There's silicon, there's germanium there. Silicon is in group 3, sorry, I beg your pardon, in period 3, and germanium is in period 4, and they are both in group 4. So that's where they are in the periodic table. They're in the same group, but basically germanium has an extra shell. Okay, now, and that explains why. So the ionization energy, is the amount of energy needed to take away the first electron. And why is it bigger for silicon? Because now it takes more energy to remove the first electron from a silicon atom because there is more attraction to the nucleus. That electron, there's more electrostatic attraction between that electron and the nucleus. Why? Because it's closer to the nucleus. Because the atom has got less shells, that electron is closer to the nucleus, and there is less shielding. Okay, these electron shells make the attractive force smaller, and germanium's got another shell, so it's going to shield that electron from the nucleus. So that's the answer. 2 marks. The production of the ionic compound calcium chloride is an important industrial process. Calcium chloride has a large range of uses, blah, blah, blah. State the name of the force between calcium and chloride ions. Well, calcium ions are positive. All metal ions are positive. Chloride ions are negative. So it's an electrostatic attraction. Yes, electrostatic attraction between opposite charges. Draw dot and cross diagrams to show the arrangement of the outer electrons in the calcium ion and the two chloride ions in calcium chloride. Okay, and I've already done this, and it's like that. Yeah, so Ca2 plus, because it's in group 2, so 2 plus. The Cl's are just Cl minus because they're in group 7. Okay, so it's CaCl2, you've got 2 chlorines, 2 Cl minuses for your Ca2 plus, and you just show the outer electrons. So the outer shell of the calcium is full, yeah, once it's lost these 2 electrons. And the chlorine, they're full as well, but you see that they've gained an electron. See the dot, yeah, the dot there, and they got that electron from the calcium. Anyway, that's what it wants. Yes. The reaction between calcium carbonate and hydrochloric acid can produce extremely pure calcium chloride, which is suitable for use in the food industry. So look at this. You've got calcium carbonate, CaCO3, plus hydrochloric acid gives CaCl2, plus carbon dioxide, CO2, plus H2O. Okay. Calculate the maximum mass of calcium chloride that can be produced when 500 kilograms of calcium carbonate, CaCO3, reacts with excess dilute hydrochloric acid. Show your working. So, in other words, if we have 500 kilograms of that, yeah, what mass of that are we going to get? That's what it's asking, assuming 100% yield. So what we're going to do is we're going to work out the number of moles of that, and looking at the equation, the ratio is 1 to 1. Like 1 mole of that gives you 1 mole of this. So if we work out the number of moles of this, yes, it's the same as the number of moles of that, and then we can work out the mass of that. So let's do it. So I've figured it out, and it's how many moles of calcium carbonate were used. Well, 1 mole of calcium carbonate. So we look on our periodic table and we see that calcium is 40.1, and it's CaCO3, so plus 12, yeah, that's the carbon, plus, and there's 3 oxygens, so plus 3 times 16. And so my relative formula mass for calcium carbonate is 100.1. 100.1 grams. Now that's 1 mole. We've got 500 kilograms of it. So 500 kilograms, now we can do it in grams or you can do it in kilograms, I don't care. So I'm going to do it in grams. So 500 kilograms is 500,000 grams divided by 100.1. And that means how many moles have we got? We have, on your calculator, 4995. 4995. I mean, to 3 sig figs, it's 5,000 moles, but let's leave it at that for the moment. 4995 moles. Yeah. How many moles of calcium chloride will be produced? Well, I reckon that is going to be 4995, because I know that the ratio is 1:1, looking at the equation. What mass of calcium chloride will be produced? Now, calcium chloride is CaCl2, so calcium chloride, calcium is 40.1 plus Cl2, so that's 2 times and 35.5 is what it says on the periodic table that we're given. So the molar mass of CaCl2 is 111.1 grams. Okay, that's how many moles we have. That's the mass of a mole. So what mass are we going to get? And to 3 sig figs, multiply them together, and I've divided by 1,000 to get it in kilograms. 555 kilograms. Yes. I think the tricky thing on this is your grams and your kilograms, getting them muddled up, so be careful. Aluminium corrodes quickly in air to form a thin protective aluminium oxide layer. That prevents further oxidation. This protective layer makes it suitable for use in drink cans, blah, blah, blah. Write the balanced equation for the reaction of aluminium in air to form aluminium oxide. The first thing I need to know, if I haven't learnt it, is what is the formula for aluminium oxide. So I'm going to start with that to start with, okay? What's the formula for aluminium oxide? Well, aluminium is in group 3, and that means an aluminium ion is Al3+, okay? Now, oxygen is in group 6, so an oxide ion is 2-. So, aluminium oxide, what do you reckon the formula is going to be? Well, I reckon if you had 2 of them and 3 of them, then you're going to get 6+, 6-. Great stuff. So aluminium oxide is Al2O3. Al2O3. That's aluminium oxide. So, balanced equation. First of all, let's write an unbalanced equation, and then we'll have a go at balancing it. So, aluminium, Al, plus O2. Now, why O2? Because it says in air. Yeah, it's reacting with oxygen in air, so it's O2. Goes to Al2O3. Al2O3. Okay, and we need to balance this. How are we going to balance it? Trial and error. You need the same number of aluminiums on this side of the equation, yeah, on your reactants as you do on here. And don't spend too long on it. You should eventually figure out that if I say we have 4Al plus, leave the oxygen for a second, 2Al2O3, and so there are 6 oxygens there, so 3O2, and that's it there. Okay, So if you look, we've got 4 aluminiums, we've got 4 aluminiums, we've got 6 oxygens, we've got 6 oxygens, and that's it. That's my balanced equation. It's practice. All I can say is practice and trial and error, and I'm going to move on now. Okay then. Most metals have high melting and boiling points. Table 1 shows the melting and boiling points of 3 metals, sodium, magnesium and potassium. Discuss the different melting and boiling points of the 3 metals and the trends that they show. So sodium, magnesium, potassium. Now you will have learned lots about trends in the periodic table. And you will have learnt, hopefully, the trends of melting points and boiling points. And if you look at this, now sodium and potassium are in group 1 and magnesium is in group 2. Sodium and magnesium are in period 3 and potassium is in period 4. Now the trends in the periodic table, hopefully you've learned, is that as you go from left to right in the same period, the melting points and boiling points increase. Now, does that agree with the table that we're given here? Well, let's have a look. So sodium, magnesium. So magnesium should be bigger than sodium. So there's magnesium is bigger than sodium, melting point. Magnesium is bigger than sodium, boiling point. So yeah, so sodium, magnesium, melting point and boiling point increase. Sodium, potassium. Now, as we go down a group, we should have learned that the melting points and boiling points get less, they decrease. So let's have a look. Is the melting point and boiling point of potassium less than sodium? So there's potassium. Is it less than sodium? Yes. And boiling point? Yes. So these numbers agree with what we should know. So I've described what the trends are. Now, explaining the trends, 6 marks, you know, we haven't got unlimited amounts of time. What are the important points? What will affect the boiling points and the melting points? This is my answer here. Okay, the melting and boiling points are determined by how strong the metallic bonding is within the metal. So do you remember metallic bonding, as in you've got all your atoms there, you know, and in a regular structure, at least in a solid, in a liquid they're not, and then you've got free electrons in between them. Okay, that's metallic bonding. And how strong is this bonding? Now, first of all, group 2 metals have got more free electrons. Yeah, they actually contribute more to this sea of delocalized electrons. So group 2 metals have got more free electrons involved in the bonding, and so it is stronger. It's like these free electrons are the glue that holds it together. And they've also got more protons in the nucleus. Magnesium has got 1 more proton than sodium, and that's going to make the bonding stronger. Yeah, the free electrons will be attracted, and the electrons on adjacent ions or atoms will be attracted more strongly because it's got more protons. Therefore, the melting and boiling points increase from left to right in a period. Now, why is the melting point, boiling point for sodium bigger than potassium? Because potassium atoms are bigger, because they have an extra shell, and have more shielding. Because they're bigger, the distances are bigger, so the forces are weaker, and they have more shielding due to the extra shell. So the bonding is weaker, and melting and boiling points decrease going down a group. So there you go. That's my answer. I reckon that's 6 marks worth.